Hello, good day. So we're back again with another lesson for our subject Engineering Calculus 2. I'm still your lecturer, Mr. Glenn F. Lucas from the Petroleum Engineering Department. So for our lesson for today, these are the learning outcomes. So number 1 is still to express calculus 1 differentiation rules as anti-differentiation rules. Number 2, apply these anti-differentiation rules and appropriate substitutions to calculate indefinite integrals. And number 3, evaluate an indefinite integral yielding logarithmic functions, exponential functions, and inverse trigonometric functions. So last time we discussed about simple power formula and simple trigonometric functions. So the format for this lecture, like last time, would be the theorems and the equations will be introduced, followed by problem solving examples. So we are more concerned with techniques to evaluate the indefinite integral, as well as familiarizing with the different patterns of the equations of the theorems that we will be applying. So without further ado, let's start. Before we go to our lesson proper, let's have another review of some useful knowledge that you have previously learned before, that is essential to be reviewed and applied for the following problems involving logarithms and exponential functions. So we have the following rules in operating with the variables with exponents, such as if a is raised to x and multiplied by a raised to y, the answer will just be a and add the exponents. And if you have exponent with a fraction, it's just equal to the nth root of a raised to m, as well as we have this ln1 must be equal to 0 and ln ab. So most if you will notice, these are just the properties of logarithms applied with a natural logarithm. ln ab will just be equal to ln a plus ln b. ln a over b is equal to ln a minus ln b, and ln a raised to r will just be equal to r ln a. Okay, so please take note of this, as you might need these properties in solving the succeeding problems. For this slide, we will just introduce the integrals which yields natural logarithmic functions. So here are the theorems and the equations. So we have, if we have the integral tan u du, it will just be equal to ln of the absolute value of secant u plus the constant of integration. For integral of cotangent u du, it's just equal to the ln of the absolute value of sin u plus c, as well as the integral for secant u du is just equal to ln the absolute value of secant u plus tangent u plus constant of integration. And we also have cosecant u du, integral is equal to ln cosecant u minus cotangent u plus c. Okay, So now let's go to some sample problems involving integrals yielding natural logarithmic functions. So our first problem is 1 over y ln y dy, the integral of that. So let's go to our whiteboard. This is our integral that we should solve for now. So solving this one, we should first write it into a clearer form. So let's transform it as dy all over y and ln y. So since we are involving natural logarithms here, we should first identify the variable that we will be assigning for this one by u substitution. So let's use u substitution and identify u. So what can be our u in this equation? So we need u, and we also need the derivative of u. So just remember that you need to brush up on your differential calculus learnings here, since you need to be able to get the derivative of a certain function in order to solve this problem. So here we will look for a particular pattern where we can apply our previous theorems to solve this problem. So for this one, it is better to assign u as ln y. So let's write u is equal to ln y. So for the derivative of ln y, or the derivative of u, that would just be equal to dy over y. So if you integrate dy over y, that will just be equal to ln y, which we already studied from the last meeting. So now that we assigned the value for u and du, we can see now that this problem is just similar to having a pattern of du, which is dy over y in this case divided by u, which is ln y. So as I mentioned earlier, we learned from before that the integral of du over u will just be equal to the ln of u plus the constant of integration. So now all we need to do is to substitute the value of u to this theorem that we learned before. So now let's just write it down as, okay, it's the same problem, so I will just proceed to writing the answer. So our answer must be ln of u, which is in this case ln y. So ln of the ln of y plus our constant of integration. So that would be our answer for this one. Okay, now let's go back. This way to start off with this solving this problem is to separate these two as two fractions. So this can also be equal to the integral cosine 3x over sine 3x plus 3 over sine 3x. Sorry, there should be a dx in here, and this should be an integral in here, dx. So let's mark this 2 as this should be the first integral, and this is number 2 integral. So for the first integral, we will evaluate it. So I did here. So we have cosine 3x and sine 3x dx. So we know from our previous lessons on identities that cosine x all over sine x is just equal to cotangent x. So knowing that, we can write this problem as the integral of cotangent 3x dx. And from our previous theorems discussed or introduced, that the integral of cotangent u du will just be equal to the ln of the absolute value of sine u plus c. So right now we need a pattern which is cotangent u and du. So for this one, we have u is equal to 3x, and the derivative of that would just be equal to 3 dx. So what we need to do is to multiply our integral by 1 or by 3 over 3, so that we can have, we multiply it by 3 over 3 so that we can have the derivative of u, which is 3 dx. So since we need 3 dx in the numerator, we will take out 1/3 outside of the integral, and we are left with cotangent 3x multiplied by 3 dx. So according to this, so right now we have cotangent u and du, which is 3 dx, and so we can solve this equation. So now we have 1/3 ln the absolute value of the sine u, which is 3x, plus constant of integration c. So that is for our first integral, this one. So for the second one, that's 3 dx over sine 3x. So let's go. The second integral would be integral of the 3 dx over sine 3x. So we will separate these two in order to get a better view how we can transform this. So we have the integral of 3 dx multiplied by 1 over sine 3x. So we know that 1 over sine 3x, 1 over sine u would just be equal to cosecant u. So we can replace 1 over sine 3x by cosecant 3x. So now our equation would be to integrate cosecant 3x 3dx. Now we will assign u, and it's better to assign u as 3x, and the derivative of u as derivative of 3x is 3 dx. So now we have here du and we have u. So this equation just becomes cosecant u du, which is equal to the ln, and the absolute value cosecant u minus cotangent u plus c. Okay, so substituting and plugging in the values, we have our answer for this one would be ln cosecant of 3x minus cotangent of 3x plus c. So now writing the answer. So we have 1/3 from the first integral ln of sine 3x plus we have the ln of cosecant 3x minus cotangent 3x plus c. So this would be our answer. Okay, so next one is, so I think this is the last one for this particular topic. So we have ln squared 3x over x, ln squared 3x over x dx. So for this one, it would be easier for us to identify what is u and what is du using u substitution if we try to separate the expressions. So for this transformation, let's separate the dx over x from the ln squared 3x. And for to better visualize, let's write ln squared in such a way: ln 3x squared, and you have dx over x. Okay, so for this one, we can safely assign u to be equal to ln 3x, and the derivative of ln 3x will just be equal to, so ln 3x, that would be du over u is 3x, and the derivative of u is 3, so the 3 cancels out, so we are left with dx over x. Okay, so pretty much it's looking like this one is our u and this one is our du. So it's looking like we're noticing a pattern here where u, this is a case of u raised to a certain power, n in this case 2 du. So we learned from our previous meeting that this is the simple power formula, so the answer is just u, the power increased by 1 divided by the same plus constant of integration. So let me just write here that our n is equal to 2. Okay, so now we are ready to substitute from the our theorem where we assign the value of u and du and find out that it just follows the theorem or the power formula, this one, u and du. So our answer would be u raised to n plus 1, that would be 3 divided by n plus 1, 3 plus c. So substituting, because this is u substitution, so we will substitute our assigned value back to u. Now we have ln 3x cubed all over 3 plus c. So this is our answer for this one. Okay, so far that is 4 problems already. So let's go back to the slides and see if we did a correct job. Yeah, it's the same. Okay, so now we have these two theorems for the exponential function, wherein the integral of the e raised to u with the derivative of u is just equal to e raised to u plus constant of integration, and this particular constant raised to u du, with this the derivative of u will just be equal to the constant raised to u all over ln of the constant plus c. So there's really nothing much to say here. I hope right now you are you notice that we are looking for the patterns, but our the most important concern here would be the technique in the identification of the u and getting its derivative du. So for example, we need to solve e raised to the square root of x all over the square root of x dx. Now going back to our board, so here, since we are dealing with e raised to the power of something, the power e raised to u, it's safe to assign the value u as square root of x, or to easier visualize, raised to 1/2. So the derivative of that is using the power formula for differentiation. So we have 1/2, we will put 1/2 here, and we will reduce the power by 1. That would be x to the negative 1/2, or let's just write it as 1/2 squared of x. Alright, that would be, or to better visualize it, 2x to the 1/2. Okay, so now we've identified our u and our du. We just need to fit this into our pattern, which says that the integral of e raised to u du will just be equal to e to the u plus c. So right now we have e raised to u, alright, multiplied by du. So what we need here is we need to have we need to multiply this by 1, which is 2/2, in order to transform it. So we need 2 on the denominator. That's why we need to put 2 outside of the integral sign to accomplish that. So now we can have e to the x multiplied by, that would be, sorry, we have here a du, a dx should be. So we have dx over 2 and x squared of x. So now pretty much we have dx to x squared of x, and that is looking much like this one. So all we need to do now is to substitute. So our answer therefore should be 2, our e raised to our u, simple as that, plus c. So there's nothing really too fancy about this problem. It's just showing how to do the u substitution and identifying which theorem are we going to use, like this one. And since we are dealing with natural exponential function, of course we will be using this pattern for this one. And the next example, we will utilize the other equation, of course, this one, so that makes it easy to make a decision what kind of theorem should we apply. Okay, so the problem is written here, the square root of 10 raised to 3x dx. So for this one, it would be easier if we express this radical symbol into a fractional form, which is, we write it down initially in the start of this lesson, how to write a radical in with an exponent in fraction form. So we have, this is 3/2 of x dx. So obviously now we are looking for u and a. So since this is 10 raised to 3 halves x, it's safe to say that a is just equal to 10, and u is equal to 3/2 x, and dx would therefore be equal to 3/2 du should be equal to 3/2 dx. So now we need to plug in all these values in order for us to properly use our theorem, which says that a raised to u du will just be equal to a raised to u all over the ln of a plus the constant integration c. So in order to get au du, so we have au and du is 3/2 dx. So we need to write our equation. Need to put 2 over 3 outside of the integral, so that we will be left with 10 3/2 x multiplied by 3/2 dx. So that looks like our original problem. If you can notice, we just multiply it by 2, which is 6, all over 3 times 2, which is 6. That is just 1. Okay, so solving, we just need to substitute a to the u, so that would be, our answer would be, don't forget about the 2/3 outside. So we have 2/3 10 raised to 3/2 x all over ln of a, ln 10 plus c. So our answer would be this will be the final answer. Okay, so that's problem number 6, I guess. So now let's proceed to, okay, so the next lesson would be to introduce integrals which yield inverse trigonometric functions. So again, these theorems and patterns are just listed here. So this particular arrangement of an integral where the derivative of u is in the numerator and you have the denominator comprised of the square root of 1 minus u squared, that will yield the arc sine of u plus c. So if you have the derivative of u all over 1 plus u squared, notice that there is no radical sign here, that would be equal to the arctangent of u plus c. And if we have the integral of du all over, here we have u outside and the radical sign of u squared minus 1, that would be equal to arcsecant u plus c. So we have 3 more patterns. So if we have this pattern where there are constants, so we have the derivative u all over the square root of a constant a squared, where a should be greater than 0, therefore a positive, minus u squared, that will give us the arc sine of u over a. So in this pattern, just remember that it is always u over a. For this one, it's just u, and there is no a involved here. So the next one is the derivative of u all over a squared plus u squared will just be equal to 1 over a, the arctangent of u over a plus c, where a must never be equal to 0. Okay, so you cannot use this pattern if you have like a du over u squared. Okay, that's a different story. So the last one would be the derivative u all over u, the square root of u squared minus a squared. That would just be equal to 1 over a arc secant of u over a plus c, where a is still greater than 0. Okay, so to tell you in advance, it's not really about the patterns. So you can always recognize which pattern you want to use, but the tip here is to have a review of your algebra, of course, and your identities, algebra fundamentals and identities, in order to transform this trigonometric functions and perform algebra, particularly since you are seeing squares here. If you can remember your lesson in algebra, how to complete a square. Okay, so let's have some examples. So this one, the derivative x all over the square root of 4 minus 9x squared. So looking at this one, I think you already have an idea which format we should be applying here. So both are the denominators inside the radical symbol are both perfect squares, 4 being 2 squared and 9x squared being 3x squared. So if you can see, we have a minus sign, so we will be looking to transform our problem into this one. So the answer should be arc sine of u over a. So let's go to our whiteboard. So now that we are here, so the first thing to do, since we already recognize which pattern we want to follow, first thing to do is to identify which is a and which is u. So in this case, the constant which should be greater than 0 is this is supposed to be a squared. So therefore a is equal to 2 and a squared will be 4. And u, remember this should be u squared, therefore, so if u squared is equal to 9x squared, if we get the square of that, that would just be 3x. So now that we have that, the last thing is to look for du. So what is the derivative of u? That would just be derivative of 3x, that would be 3. Okay, so we already identified initially that we will be using the pattern du all over the square root of a squared minus u squared, which is equal to arc sine u over a plus the constant of integration. So what is the missing piece here? So I think the missing part is we need to write this one down as du over square root of a squared minus u squared. So the denominator is already good. That's a squared minus u squared inside a radical symbol. But the numerator should have 3 in there. So what do? We put 1/3 outside of the integral sign, and we can write 3. Sorry, this should be 3 dx. You can write 3 dx here, and our pattern is complete. Sorry, that should be, I should write the true variables. So that would be 2 squared minus 3x squared as well. Okay, so plugging in the values, we have 1/3 outside, so we have 1/3 the arc sine of u all over a plus the constant of integration. So we have 1/3 arc sine 3/2 x plus c. That is our answer for this problem. Now let's go to our next problem. Okay, this one is a particularly tricky one, but as you can see, we don't have any radical signs in there. So if we will go back to our theorems, this might be our choice since there is no radical symbol, or we cannot really use this because there is no constant here, it's just 1. So I think our best shot would be this pattern, this one, which is du over a squared plus u squared equals 1 over a arctan of u over a plus c, where a is not equal to 0. Okay, so we can see that we don't have any a which is 0 in that pattern. So let's see how we can transform our denominator into such as this, which is a squared plus u squared. Okay, so this is our problem. Let's go to our whiteboard, and okay, so we have dx all over 3x squared minus 2x plus 5, and we need to integrate that. So as we already mentioned, we want to transform this one into a pattern that we can integrate and that we know, and that particular pattern is the one with a squared plus u squared, and that is equal to 1 over a, the arctangent of u over a plus c. So now we have to identify which is our a, which is our u, and what is our du. So first let's write it. So in order to get a square in the denominator, we need to remove or factor it by remove the constant 3. So let's write it down as dx all over 3. So let's remove the 3. So what's left is x squared minus, this is, since we remove the 3, we divide this by 3, so that's 2/3 x, and the last term should also be divided by 3. So this is not yet a perfect square, so we need to do is to complete the square. So next step would be to keep the 1/3 outside of our integration sign. We have dx here. Okay, so we are left with x squared minus 2x plus 5 over 3. So this doesn't look anything like a perfect square, because if you can remember this pattern in algebra, this should be x squared minus 2x plus 2 squared, which is 4. So we have now the idea that in order to complete this square, we need to have, or we need to add, this is 2/3 divided by 2, that would be 1/3. Okay, So now we write, this is our squared now, x squared minus 2 third x plus 1 third. So since we added 1 third, we also need to subtract 1 third so that we won't change the equation. So originally we have 5 third, so we just I'm sorry, this should be 1 third squared, so this is 1/9. Let me erase that. This is 1/9. So let me write 9 in there. Okay, so since this is 1/9, we also need to subtract 1/9 from it. Okay, so let's simplify this one. This would just be, let's write 1 third the square root of, the integration of dx all over, let's write this in square notation. So this would be x minus 1 over 3 squared, and let's check, this is x squared minus 2 third x plus 1 third squared, that would be 1 over 9. Okay, so we have that one correct. So next is 5 third minus 1/9. So that would just be our least common denominator is 9. So 9 divided by 3, that's 3 times 5, that's 15 minus 1, that would be 14 over 9. Okay, so now 14 over 9 should be our constant squared. So let's write this again in such a way where we can see the roots. So this is 1 third dx all over, this is our u. So again, the order doesn't matter. In our pattern, we have a squared minus u squared, but we can write it down as u squared plus a squared, as the case is right now. So our u yung nauuna, plus this should be the square root of 14 over 9, or since 9 is a perfect square, that would just be equal to the square root of 14 over 3. Okay, so now that we already identified, we transform the equation. We didn't change anything actually. If you will perform the operations, this will just still be equal to this. So we didn't change anything. We just need to visualize it in a way where we can identify a pattern so that we can apply the theorem and get the evaluate the integral. So now let's write which is a and which is u. Okay, so from that we already identified that a is equal to the square root of 14 all over 9, and a squared is equal to, the square root of 14 over 3 over 3, and a squared would just be equal to 14 over 9. We also have u, which is equal to x minus 1 third, and our u squared of course is x squared minus 2 third x plus 1/9. So for the derivative of u, so the derivative of x is 1, the derivative of 1 third is none or 0. So this will just be equal to dx. So writing the equation, let's go back to there, and our pattern is 1 over a arctangent. Sorry, so okay, so we don't have a problem. We don't need to imagine fractions now. We just need to directly substitute. So 1 over a arctangent u over a plus c. So our answer would be 1 over a all over a, which is square root of 14 over 3, the arctangent of u over a. U is x minus 1/3 all over the same thing, square root of 14 over 3 plus constant of integration. So at this point, we want to rationalize everything, and we don't want any radical symbol in the denominator. So what we're going to do, okay, let's write it down as, so the 3 goes up, and this is square root of 14, the arctangent, the 3 goes up, so this would become 3x minus 1 all over the square root of 14 plus c. So since we will not rationalize it, we will multiply it by square root of 14 over square root of 14. So this one would be 3, the square root of 14. So the denominator, square root of 14 by square root of 14, that would give us 14. So arctangent, this again, we multiply 3x minus 1 by square root of 14 all over 14 plus constant of integration, and the problem is solved. So we have our answer now. So this is our answer for this one. Okay, looks like I missed something. Let me, okay, so we have 1/3. Please pardon, we forget about the 1/3. We need to multiply this by 1/3. So it means that if we multiply this by 1/3, the 3 here will just cancel out. So I'm sorry about that. Please be very careful about the constants that we are leaving out of our integral. So in the end, you should be able to include them in your answer. Okay, so I think this is problem number 8, and we are down to our last example. Okay, so our last problem is this one. Okay, so if you can see, we have an expression in the denominator. We have an expression multiplied by a term which is inside a radical symbol. So if we will be looking for we should be looking at a constant in a and a u. So okay, so I think this is our guy. So derivative of u over u. So we want now to transform that equation in this one, du over u all over u squared minus a squared just equal 1 over a arcsecond u over a plus c. Okay, so let's see if we can do this. and we want to find an easy way how to do it. So let's go to our whiteboard, and this is our problem. So we have 6 dx all over 2 minus x, square root of x squared minus 4x plus 3. So initially, what I will think here, if you want this to be your u, you cannot take this form such as this, 2 minus x. So we need to inverse this, multiply it by -1. So if we multiply it by -1, this will become x minus 2. So since we multiply it by -1, we need to put -1 here as well. So I will also put -1 times 6 outside of the integral sign. So now we have dx all over x minus 2. So this became x minus 2 because we multiplied it by -1. And for us to be able to multiply it by -1, we also need to have a -1 outside here. So that's why it's -6. I hope you can follow that. So since we are trying to make this one as our u, and we want u squared inside of this, so we have x squared minus 4x. Okay, that's, and we have 3 plus 3, but this one, if we square this, we need this to be x squared minus 4x plus 4. Okay, so since this is plus 3, we only need to add 1 to complete the square. So let's add 1, and we cannot add 1 by, if we will not subtract 1 as well. Alright, so this one, let me write it again here. So we have now -6. Don't forget about that number, our constant, all over, this is x minus 2 multiplied by the square root of, we already said that this is x squared minus 4x plus 4. That's -2 times -2. So that is our desired u squared, and we have -1 left. So in our pattern, it is u squared minus a squared. So this look like this all seem to go according to our plan. So now let's identify what is and what's not. So first of all, the thing we forced is that u is x minus 2. U squared would be this one, that's x squared minus 4x plus 4. Our a is, since it's minus a squared, a is 1, and a squared is also 1. Now we're looking for the derivative of u, which is u will just be equal to dx. Okay, so now applying this, and we already said that what the pattern we want is du all over u multiplied by u squared, square root of u squared minus a squared, that will be equal to 1 over a arc second of u over a plus c. So now let's go to next page and substitute everything. So now, please don't forget about our -6 outside. We have a equals 1, so we have 1 over 1, the arc secant of u. Our u is x minus 2 all over a, which is 1, plus c. So to simplify, our answer is negative 6, the arc secant of x minus 2 plus constant of integration c. Okay, so this is the answer for this particular problem. Okay, so now that we all solved our examples, so I hope that you get that what matters here is, first of all, your fundamentals. As you can see, you will use identities, you will use completing the square, you will use properties of logarithm. So please brush up on those, and of course be familiar with the theorems introduced here in the introduction of anti-differentiation. So right now we covered logarithmic functions, natural logarithm, exponential functions, as well as inverse trigonometric function. So the pattern is really it's not easy to find, but if you know how to manipulate your equation and transform it, identify the u, get the derivative of u, and as well as the constants a, and identify the proper pattern, then you won't be having any problem. So that's all for this discussion. And for our sources, we're still using the calculus by Leithold, and you can Louis Leithold, and you can find this chapters if you want to read it in the book, page 439 to 501. Okay, so now thank you for listening. I hope you got something and learned new things here in our class, and good luck on your activities. Thank you.